So I thought, in this workshop everybody is going to talk about graphs. They are going to talk about how to do inference on graphs, how to generate graphs. We have heard a bunch of very interesting talks the whole day. So I am going to take a different tack, right. So what I am going to talk about is how do you exploit the computational structure, the access pattern graph of a machine learning problem in order to scale things out, right. So this is machine learning and graphs. So this is, I am not using graphs, I am not generating graphs, I am not doing inference on graphs, I am using the access pattern graph, but on a machine learning problem to see how to scale things up. Okay, so that is what the agenda is. And so the key question or the challenge is, if you want to use Bayesian methods, the common thing or the common sort of theme that you see is that many of the experiments are on small scale data sets, because and especially if you go to the industry and you talk to people will say, oh, but Bayesian methods don't scale, it's hard for me to run it on large industry scale problems. So therefore I'm just going to do something simple, I'm going to use some kind of logistic regression or so on. So the question that we wanted to ask is that can we really scale up these Bayesian models? And when I am talking about scaling, I am not talking about sort of system scaling, right. As I am not talking about, oh, let's take a bigger Hadoop cluster and spread it across 20 data centers and or take out every single clock out of the CPU. So that's sort of system scaling, and that's one part, but what we are talking about here is algorithmic scaling. So can we understand something about the structure of the underlying problem, the structure of the objective function, and can we use that to get what I call algorithmic scaling, right. By understanding the structure, can we do better? So I will talk about two particular models that we have looked at, and where it turns out that you can exploit similar kind of algorithmic scaling. And actually this is sort of surprising, and this is something that I have been working on for the last 1 or 2 years, is that this kind of structure is something that is present in not only these kinds of Bayesian models, but across a variety of other different models in machine learning. So if you are interested in that, please come and talk to me. But today I will talk about two things. One is the mixture of exponential families, and the other one is LDA. So again, what I would urge you to do is that as I am walking you through the equations, most of them are basic. I am sure 90% of you have seen them. For the 10% who haven't seen them, don't worry about the math, but follow along the intuition. Okay, so with that caveat in mind, let's look at what does the graphical model for a mixture of exponential families look like. So you have your data, right, and then the data has some sort of there is a mixture model. So these are some of the parameters of the mixture components, and then there is sort of a mixture proportion, so which says that how much proportion of each of these parameters is present in your data, and then associated with each data is sort of a latent variable which tells you which particular component it was picked from, right. So I mean, sort of, if you want to if you don't know anything about mixtures of exponential families and you want to keep an idea in mind, think about k-means, right. So these are the k centers in the k-means, these are the proportions, and this tells you which center this data point is associated with, right. So just to sort of simplify things. So the generative model here is that you first draw the mixture proportions from a Dirichlet, and then you draw the k samples, the k cluster centers, and then for each data point you are going to first go and draw the z tells you that which of the k components this data point came from, and then you will draw from that particular exponential family distribution, okay. And we are going to make all the nice assumptions about conjugacy in the priors to make our life simple. You can extend it to other things, the math just becomes more hairy. So let us keep ourselves to the simple situation. So the joint distribution of the parameters conditioned on everything that is observed can be written out. You can just read it off from the graphical model, and basically what we want to do is we want to estimate from the joint, we want to marginalize out the data, and we want to estimate the posterior of the parameters, right. So this is what you want to do. Now if you look at this posterior, the posterior is a difficult to estimate beast. It looks really horrible in some very high dimensional space, and you don't know what to do. So one possible thing that you could do is you could say, let me pretend that actually there are the parameters are sort of conditionally independent. So I am going to make a certain set of simplifying assumptions, and then I say, given that if I assume that these kind of independence assumptions existed, what is the best distribution that will describe, or which is the closest to my posterior, right. So this is sort of if you are an optimization person, you are saying that, okay, I am going to assume that the Hessian is diagonal, and then given the condition that the Hessian is diagonal, what is the best fit I can make to a function, okay. So that is one way to think about it. So then the graphical model now for the variational version of things looks like this. So what you end up doing in real, and this is, so you quickly transform it into an optimization problem, and this is the place where I like to play. So the optimization version of the problem says that I am going to minimize the KL divergence. So if I ask you, what is a measure of distance between two distributions, one of the things that you can consider is to take a KL divergence, right. So now what you are going to, what we are saying is that we will take the KL divergence between the two distributions, the true posterior versus what we want from this sort of factorized version, and then let us try and optimize this, right. So now if you look at this objective function, so the objective function has essentially three things that you are trying to estimate. So you are trying to estimate the pi, which is the proportions, the theta, which are the cluster centers or the parameters of the cluster centers, and then the z's, which are the assignments, okay. Now what we really want is, if we want to do this on a single machine, life is good, but what we really want is an algorithm which is distributed, asynchronous, and can scale to very large data sets, okay. So this is what we are looking for. So in order to do that, let us first understand how things are done, and then let us go down a path and see whether we can understand the access pattern graph, and if we can understand the access pattern graph, can we use that to actually make better, to distribute the algorithm, okay. So this is what we are going to do. So if you look at traditional variational inference, again if you show it to an optimization person, they will say, oh, all you are doing is block minimization, right, so in some sense. So this is what you end up doing. So you have three sets of parameters, so you start doing block minimization. So you fix your theta and your z, and then you start optimizing your proportions. Then you fix your proportions and your assignments, and you optimize your cluster centers, and then you fix your proportions and your cluster centers, and you optimize the assignments, right. So again if you think of the k-means analogy, then you are saying this is sort of the cluster assignment, this is you are recomputing the clusters, and this is the place where you take each data point and then you reassign it to a new cluster, okay. So this says what proportion of data points go to each cluster, this is the cluster center estimation, and this is the reassignment of the data points to the new clusters, okay. So again just to keep this in mind. So now if you look again at what happens inside each of these steps, so to compute the cluster proportions of each data point, basically again think of the k-means analogy. So you go there and you find all the data points that are assigned to the cluster, and you say what is the fraction of them that are assigned to each one of these each of these clusters. So if you look at the access pattern, this is what we are interested in. So you have your data, so this is your data, these are your centers, right, and this is your fraction, the pi parameters that you are estimating, and these are your assignments. So what you end up doing is that you take all the data points, look at their assignments, you sum them up. So basically you sum up the columns of this matrix, and that basically gives you the entries of pi. So if you think from an access pattern viewpoint, what you are doing is you are updating. So anything that is shown here in red means that variable is being updated. Anything that is being shown in green means that variable is being read, you are reading that variable, and anything that is in white means that you do not care about the value, so they do not participate in this operation. So in order to write, or in order to update pi, you need to know all values of z, right. So keep this in mind. Next, when you want to update the centers, the cluster centers themselves, then essentially what you end up doing is you take all your data points and you say, I am going to compute an average of all the data points that are assigned to that particular cluster, right. So the same thing happens here, just like what you would expect in say a simple k-means like algorithm. So you have your cluster centers. In order to update your cluster centers, you need to know what are the data points and what fraction of a data point is assigned to each cluster, right. So this is sort of the two pieces of information that you need. Given that, you can update the cluster centers, okay. So again here you need to read these two pieces of variables and then you update the thetas. And then in the when you are reassigning data points essentially to each cluster, then here what you do is you have to look at essentially you have to take each, you have to read each of the cluster centers and then you have to assign each of the data points to the particular, to find out who is your nearest neighbor and you have to assign it. So the same way here a soft assignment happens, but pretty much the intuition remains the same. Okay, so then to find out the proportion of each data point in each cluster, you have to know the cluster centers and then of course you have to know that particular data point and you need to know the assignment, the pi. Okay, so you need these three variables and you update this variable. Okay, so one thing that you would have noticed is that here you update the theta and the pi are the global variables and z are local variables. So the z are local assignment of clusters to individual, the local assignment of data points to each individual cluster. Okay, so the local assignments are done in a batch process. So you first get all your centers fixed, you find all your pi's and then you assign each of the data points, then you go back and you re-update. Instead the stochastic version, the stochastic variational inference, what they end up doing is they say let us update the global parameters, then we pick one data point, we update its assignment, then fix those assignments, then go back update the global parameters and keep doing this. So the idea is that you get multiple updates to the global parameters as you are streaming through your data, and the claim is that this leads to faster conversion. So now again if you look at the access pattern for this particular kind of updates, you will see that you pick one data point, you take the assignment of that data point, based on that you update the parameters, the pi, then you pick the new assignment and that data point again and you update all the cluster centers. Then having updated all the cluster centers, you go back and you update the assignments of each of the data points, right. So sort of you go through this iterative process. The key problem however is that if you want to do something like this and you want to distribute the computation, this is a step which is a key bottleneck, right, because you need to have on every machine or whenever you are updating the cluster centers, all the cluster center, so whenever you reassign a point, every single cluster center changes. So you need to have that in each of your local machines in order, in your local machine in order to do those computations, right. So this is something that you want to avoid. So if you want to distribute your computations and you do not have access to all the cluster centers in all the machines, so how are you going to do this, right. So this is the key question. It turns out that there is a sort of a very simple and sort of simple observation here, is that suppose let us say I am going to take things to the extreme and instead of reassigning taking one data point and computing its assignment to all possible clusters, what I am going to do is I am going to take one data point and only adjust its proportions in a small fraction, in particular just two clusters. So I am just going to take a data point, I say what fraction of it is assigned to these two clusters and I am just going to change those proportions, okay. So and then I am now what that means is that just for those two local clusters the cluster centers will change, so I have to update that and then of course the proportions will change and I have to change that, right. So let us see how the access pattern now looks like. I take just 2 points and I am updating, I am just taking 2 clusters and I am updating them. So I get these 2 clusters and now I am only updating the global parameters corresponding to just those 2 clusters. When I do the theta update, now I am only updating the cluster centers corresponding to just the 2 centers that I touched, everything else remains same. And when I am updating reassigning the data points, since only 2 cluster centers change, I only have to reassign the data point to just those 2 centers. Okay. So now if you look at this computational graph, there is one very big advantage if you look at this graph, is that these so first of all the question is, okay, does this converge? I mean, you know, if you, instead of doing this stochastic version, if you do this sort of extreme stochastic version, does it converge? And the answer is yes, and actually pretty much it converges. You can't even see the difference between variational inference and stochastic variational inference and extreme stochastic variational inference, because they're pretty much converging at the same rate. Okay, this is on a small data set. And but the key insight here is that all of these updates can be done in parallel, right? Because if you look at the access pattern graph, basically you are teasing it apart and finding sort of these independent sets or independent components, and you can perform updates in parallel, right? So let's see how this is done. So let's say you have 3 processors, okay? So the 3 processors, so processor 1 could be updating this part of the Z matrix, so could be reading this part of the Z matrix, the other processor is reading this part of the Z matrix, and the third processor reads here, and they are updating these different versions, these different entries of pi. For the theta update, again these 3 matrices are reading data in this part of the from X, and then they are updating these corresponding Z assignments. They are reading these corresponding Z assignments, and then they are only, because only the cluster centers that are only 2 of these cluster centers have changed, so actually they can perform a local update to just those 2 cluster centers on their own, right? So, and then the same thing happens for the pi updates, right? So once again, just to show you this sort of more graphically, how would you distribute the computation? You take your data, you would stripe it across 3 machines. So in this case you have a purple, a blue and a yellow machine, and you take your Z matrix and you would stripe it across the 3 machines, okay? So and then you take your theta and again stripe it across 3 machines, okay? And for a minute, I'll tell you in a minute how to keep the pi in sync. It's only a very small vector which needs to be kept in sync across machines, but for now just pretend that you can keep it in sync. So you start off with this. So what happens is that the green, the blue, the purple machine can do any updates to this part of the Z matrix, and it can do any updates to this part of the theta matrix, right? And it can, we are going to assume that it can update any of the pi, and I'll tell you how to keep that in sync. The blue one can do any updates here and here and here and so on. Then when you are done with one of the cluster centers, say the purple machine might decide, the yellow machine might decide that it is done with that cluster center, it will send it asynchronously to the purple machine. So now the purple machine gets that and it says, oh, I can now perform updates on that part, I can update that center myself because I own it, and I can also update the cluster assignments for that, for the set of data I own. So now the theta variables keep on moving through the network, and they keep on getting updated by individual machines, and they move on to different networks. The Z matrix remains striped in the different machines, the data remains striped in the different machines. So the data never moves, the Z matrix never moves, and various rows of theta keep on moving through different machines, and they keep getting updated, okay? And now I have to show you how to keep the pi in sync, which is the last bit that you need now to make this massively distributed and also asynchronous. And so actually it turns out that pi is a very small vector, it's only of size k, where k is the number of clusters that you are learning, the number of components that you are learning. And so all you need to do in this case is that you have to send a message in a round robin fashion from one machine to the other. Pi does not change a lot because it's an aggregate, it's a summation over each of the, over what is happening to each of the machines. So pi actually doesn't change a lot. So you can just send it in a round robin fashion. So modulo this pi update, everything is exact, everything is happening asynchronously, and everything is happening in a distributed fashion, right? So and now you can massively distribute your computations. You don't have to wait for synchronization, you don't have to wait for any of the processors to synchronize at any point of time, okay? And so this is very new work, I have to apologize for that. I am very excited by this, but we don't have a lot of large scale results to show. I will compensate for it in the next part. But you know, usually these are not the numbers that you would see on my slides, but I just want to give you just an idea. So this is just a synthetic data set with 5,000 data points in just 2 dimensions. But I believe we do have a few more other ones on simple data sets like MNIST, but stay tuned for results with larger data sets. But sort of the idea that I wanted to convey here is that if you understand the computational structure, if you understand the access pattern graph, then you can really scale things up, okay. So to sort of compensate for this sort of small things, let me actually show you possibly the most scalable LDA sampler that exists, okay. So let me show you something about that. So let us go to LDA, and again it turns out that the computational structure, the access pattern structure, is actually almost identical in the case of LDA versus and also in the mixture of exponential families, right. So and with a very different algorithm. This is basically even when you do not just variational inference, but when you do something like collapse Gibbs on LDA, the access pattern, the computational access pattern remains the same, and we can exploit the same observations, okay. So just to give you a very sort of high level overview, in LDA you assume that you have a set of topics, and the topics are a multinomial distribution over your words, right, and then each document has an underlying topic distribution, so it is a distribution over the topics, and then whenever you draw a word by first sampling from the topic distribution, then finding a topic and then sampling a word from that distribution, right. So the graphical model looks like this, and actually the generative process is also fairly similar. It's again it's almost similar to the generative process for the mixture of exponential families, except that here every dimension is drawn independently, while in a mixture of exponential families all the dimensions are drawn at once, okay. So the key idea again is the same. So you draw your topics from a Dirichlet, you draw your for each document you draw your topic proportions from a Dirichlet, and then for every word you draw from a multinomial, okay, and then you go to the particular topic and then you draw a word, okay. So as before, it's the same story. You have a joint distribution, and if you look at the collapse Gibbs sampler, and this is where things get interesting. So the collapse Gibbs sampler, the basic idea again is that you have you are maintaining the assignment vectors, or right, and the assignment to resample the assignment vectors every time you look at these. Essentially again let us go back and look at the access pattern. So right, so you are maintaining the number of words that have been assigned to each of these topics, and the number of words that have been for each document you maintain how many of the words have been assigned to each topic, and for each word you keep account of how many times this word has been seen in each topic, right. So these are the two vectors, and then of course there is the summation of this matrix, this NT, which is kept, right. And again if you look at the computational structure, it is pretty much the same. If you pick a word from a document, then the two vectors that you need to access are the document to topic vector and the word to topic vector, right. So if you have these two vectors, you can resample the word and you can move on. So what this allows you to do is you can do the same kind of computation where you can take many different processors and you can run these updates in parallel, and you can synchronize, okay. And it turns out that this plus you have to do a little bit more, which I am not talking about, is that because especially when you have very large corpus, the number of topics is very large. So if you just use plain sampling from a multinomial distribution, it is usually very slow. So you have to do a little bit more. You have to use something called a Fenwick tree data structure, but modulo that, it turns out that you can massively distribute this computation, and I will show you two sets of experiments. One is on a single machine but multi-core, and then the second one is on multi-machine. And this is PubMed, which has 9 million documents, 700 million tokens, and these are from the Amazon reviews. So this is 30 million documents and about 1.5 billion tokens. And on a single machine with about 20 cores, you can see that on something like the Amazon dataset, I think in less than an hour or so, we are able to learn, and this is, I think the number of topics here is 1024. So we have a fairly large number of topics, large number of tokens, and large number of documents. And I think in less than an hour or so, you are able to get a fairly decent LDA sampler on a single machine. And then this is on a multi-machine. So there are 32 machines. Each machine has 20 core processor, 1024 topics again. And again, this is the Amazon dataset. And then the UMBC is a larger, slightly larger has a slightly larger number of documents, but fairly similar number of tokens. So again, 1.5 billion tokens. And again, you can see that compared to other methods which distribute the computation, by being asynchronous and by exploiting the access pattern graph, you can actually do significantly faster. So to conclude, I just want to say there is a lot of interesting things that you can do at the intersection of optimization, machine learning systems, parallel programming and theory. And if you pay attention to the access pattern graphs, if you pay attention to the computation graph, there is a lot that you can gain by doing this as well. There are so the LDA paper appeared in www, and the extreme SVI paper is available on arXiv. You can play with the source code. You can find it online. If not, send me an email and I can give you links. I want to acknowledge my collaborators, Inderjit Dhillon from University of UT Austin, Shihao Ji from Intel Labs, Cho, who is at UC Davis, Hsiang-Fu, who is at UT Austin, Params, who is at UC Santa Cruz, and Yun, who is in Amazon. If you have questions, I'm happy to take them.
Thank you for the presentation. My question was for the second part of your talk, for the LDA. So you showed something that around 1,000 topics or something. So my guess is that you're making the assumption that the topic matrix, topic document matrix can actually fit in the memory of one machine. I was wondering if you have experimented with really large matrices where you might have like more than 1 million topics.
Oh no, I mean so this is completely. So let me go back. So the structure in LDA is pretty similar to this. So we do not assume, so the topics do not fit on a single machine. That would be disastrous. Right. Yeah.
Cool. Thanks.
Thanks. Yep. No, X is striped. So data is striped. You never move the data. Again, that would be disastrous if you moved the data, right? So data is distributed once, and that's it. Yeah. So every machine has a copy of has a stripe of X, and it has the Z matrix. And every machine has a subset of the theta, and there is no overlap. So no machine, there is nothing that is duplicated. Right? Except for the pi, which is a k-dimensional vector.
So you mentioned that the variational inference and both variational inference and give sampling, right? Did you compare them on LDA using both approaches?
Yes. So I mean, so our work is not about whether variational inference is better than give sampling. So we work on the optimization or the sampler layer. So the answer is so from an optimization, from our algorithm perspective, whether you do give sampling or whether you do variational inference doesn't matter. The algorithm still applies. Whether give sampling is better than variational inference, that's a sort of modeling question, right? So that's not So we are the algorithm, we are the optimization layer, we are the sampling layer, we are not the modeling layer. Does it make sense?
More time. So it sounds like your optimizations are working at the theoretical level of the access patterns for any model that would be doing this access.
Yeah.
But I'm wondering if you could look at the specific updates adaptively as you were doing optimization within a specific model and make even further gains at that point.
Yeah. So one of the things that we have talked about, for instance, is that right now our data is striped once and for all, and that's it, right? And then your parameters move. So one of the issues for, especially this happens in Gibbs sampling for LDA, is that some words are very popular and some words are not as popular, right? So, but since we already striped the data and we know, I mean, we are sort of committed to not moving the data, we don't take advantage of the fact that, you know, if by chance all the heavy words happen to land on a stripe where all the heavy documents are, that's a bad thing because everybody has to wait, and that is something that we have talked about. But always the trade-off is, are you willing to move data in the middle of the optimization, right? And that's you know, usually I haven't seen yet a data set where, you know, like where moving the data would justify the cost. But on the other hand, it is true that when you get really heavy words to sample, you know, that particular machine is slowed down. But because things are asynchronous, that doesn't slow down everybody else. So that's the advantage. That's a sort of redemption factor. Yeah.
All right. So let's thank the speaker.